I'm just trying to get this, trying to get my window to do the right thing. Okay, so this time I'm going to try sharing the entire screen, which means I won't see the chat or the Zulip. And I would encourage, you know, if a question goes up, then someone can jump in and let me know. Or someone can just jump in and ask the question. But then what would be good would be if later on we write up these questions in Zulip, and then I can answer them properly. So let me try sharing the screen again. Okay. So how are we going with this? Good. All right. Part 2. What we want to do in the next hour is look at some actual protocols. What we want to do is, first of all, look at key establishment. So we'll do this using elliptic curve Diffie-Hellman, but in particular, the way that it's done right now in the state of the art, which is X25519. Then what we want to do is look at signature schemes. We're going to look at Schnorr signatures as the general framework. After, if we've got time, we've got slides on EdDSA and on ECDSA. But if we don't have time, there'll just be bonus tracks at the end. Okay. So Diffie-Hellman is something that everyone thinks they know, but what I want to do is explain the way that you're actually using it in your web browser, or at least the elliptic curve algorithm at the bottom of all of that. So we really need key agreement in cryptography. I think everyone here can agree on that. And the classic protocol for doing this is Diffie-Hellman key exchange. And historically, this is interesting because it's basically the first asymmetric crypto algorithm. Okay, it's 45 years old, or nearly 50 years old right now. So this has certainly been around longer than most of us have been alive, or algorithmically sentient anyway. So we've also got chems, and I was going to put some chem slides in, but well, there were already too many, so I'll either add them again later when I post these, or we'll leave them out completely. Okay, so keys come in matching public and private pairs. Okay, so you've got a public key and it's matching a private key. And that's your key pair. And your key pairs might be long-term, in which case you'd say you've got like a static key pair, or they might be single-use key pairs, which is ephemeral keys. And every public key poses an individual mathematical problem. And this is like a general thing in public key crypto. Every public key is posing an instance of a mathematical or algorithmic problem. And then the private key is giving you the solution, essentially. So in the discrete log setting, which we've presented earlier this morning or this afternoon, our key pairs represent discrete log instances in your prime order group. So now we're just going to suppose that our group G with a generator P, we're going to say it's prime order. So of course it's therefore cyclic as well. So the public key is going to be Q, the private key is going to be X, where X is the discrete log of Q to the base P. So Alice and Bob want to establish a shared secret with no prior contact. And in Diffie-Hellman, the idea is that they're going to combine their secret scalars from both sides. So Alice and Bob both have a key pair. They can see each other's public key. And what they're going to do is combine the secret scalars using composition of scalar multiplications. There's just one thing that I want to mention before we go on with this. Which is that this protocol has no built-in authentication. Okay, so at the end of this protocol, Alice and Bob will have a shared secret, but they won't necessarily know that Alice and Bob really are Alice and Bob, right? So either we're going to pretend that this is all done over a channel that's been authenticated, but it's not a secret channel. So they basically want to add secrecy to an authentic channel, or they're going to have to just do this and then sort out authentication after the fact. You know, play some other game or add extra layers of a protocol, or do something out of band to authenticate what's going on. So this is really just establishing a shared secret, and that's it. And the protocol works like this. Alice generates her key pair. So public key Q, private key X, X being the scalar, which P times XA will give you QA. Bob has a key pair on his side. Time is moving downwards in these diagrams. So if something's happening towards the top of a box, it's happening earlier. These red dotted lines basically representing some sort of synchronization, or like a beat in time. So above the line, this happens earlier, and below the line, this happens in a second phase later on. All right, so they've each generated their key pair. This could be like a ephemeral Diffie-Hellman where Alice or Bob is doing this in response to a connection from the other one right now, and they're going to compute the shared secret right away. Or it could be like a static Diffie-Hellman where they computed these keys last year, or they generated them, I don't know, years and years ago, and now they're going to have to compute the shared secret here. So they do this by each one takes the other's public key and multiplies it by their secret key. This is going to give an actual shared secret because scalar multiplications commute. So Alice is taking QB, which is XB times P, and then multiplying that by XA. So she's got XA, XBP as her value of S. Bob symmetrically is going to have XB, XAP, but XA, XB is XB, XA. So there you go, they've derived the same value. Then what they do is they take this shared secret, which for us is going to be like a point on an elliptic curve. A point on an elliptic curve is not a cryptographic key. Okay, I mean, it might be a public key with respect to some crypto system, but it's not like you can use this as a key for AES encryption, for example, which is probably what they want to do next. So what you have to do is apply a key derivation function, basically hash the point to get a shared, well, cryptographic key based on this shared secret S. And that's a really important point. Okay, so Diffie-Hellman security depends not directly on the DLP, but rather on the computational Diffie-Hellman problem, which is given all the information that we can see in public here. I've got a chunk of Zoom window that I can't get out of the way, so I can't see what I'm doing here. All right, so given the public information, everything that's in Alice's box is private to her, everything in Bob's box is known to him, and then out here in the middle is just the internet, the wide world. So everyone knows this stuff. So we all know the base point P, because that's a system parameter. We all know QA and QB. And so the computational Diffie-Hellman problem is given this stuff to then work out what the shared secret was. All right, so that's a problem which you can obviously solve by solving discrete logs. Like take Alice's public key, work out the discrete log XA, and then you can impersonate Alice after that. You can take Bob's public key, multiply it by the XA that you know, and you'll have the shared secret. So in that direction, it obviously works. There's an immediate reduction from the Diffie-Hellman problem to the discrete log problem. You can solve a Diffie-Hellman problem by solving only one discrete log. And in the other direction, you wonder, well, it's not at all obvious how to go backwards. You know, if you had an algorithm that solves Diffie-Hellman problems for you, how do you use it to compute a discrete log? Okay, I mean, we know that the Diffie-Hellman problem is no harder than the discrete log because we have this immediate reduction. But going in the other direction, you know, you want to know that the Diffie-Hellman problem isn't massively easier. So there is a conditional polynomial time reduction, and I put it in the bonus track of the part 1 slides, if you want to look into this for a bit more detail. The conditions are kind of mathematically implausible, but they still work in practice, which is kind of cute. But if you relax them and you allow yourself an unconditional, well, allow yourself a sub-exponential reduction, then you can make this unconditional. Okay, so even if it's sub-exponential, I mean, you're using this basically to beat an exponential algorithm, so it's fine. You know, that's probably good enough in theory. In practice, we managed to get what we need to do the original reduction for like cryptographically relevant parameters. But that's there are some references and whatever in the slides for part 1, and I'm happy to discuss that basically all week. That thing. But this is the Maurer-Wolf results. Basically, this is why we tend to act as if these problems have the same difficulty, even though they're clearly not the same thing. Okay, so back to Diffie-Hellman. Alice and Bob, I mean, so far we've just taken something straight out of a textbook. They've got a group, they do some scalar multiplications, they throw their public keys out there. Then later on, they retrieve the public keys they want, they multiply by their private scalars, and now they've got a shared secret. But when you look at this protocol, you notice that, that it never actually uses the group structure on G, okay, on the group. Like nowhere in this picture do you see a plus anywhere or a minus. All you see is scalar multiplication. This key pair function, I mean, it's just using scalar multiplication as well to generate a key pair. It's sampling a random scalar and multiplying the base point to give us the resulting public key. Okay, so what really matters here is scalar multiplication, and there's no group in here. So long as, well, there's no explicit group operation. So long as we have something that has a bunch of things that look like scalar multiplication, then we can still do Diffie-Hellman. Okay, so what we really need is some set G, and then big randomly samplable sets of efficiently computable functions, one set for Alice to sample from, one set from Bob to sample from, they can be the same, okay? Such that whatever they sample, it's going to commute afterwards, and the corresponding Diffie-Hellman problem is believed to be hard. Okay, I mean, you can mathematically, you can define this all you want, but if you can't come up with examples where the Diffie-Hellman problem doesn't look hard, then it's no use at all. Right, so we don't need a group law, just scalar multiplication. So we can drop the signs and work modulo minus if we're working on elliptic curves. Okay, what that means is, when I say drop signs and work modulo minus, I mean, I'm saying that a point and it's negative, or a group element and it's negative, I'm going to consider to be the same. That's something that's completely compatible with scalar multiplication, because if you do m times a point and then negate, or if you negate the point and then do m times what you, well, the result of that, then either way you're going to end up with minus m times the point. Okay, the minus commutes with the scalar multiplication. It just moves across to the other side. So what that means is, you know, mathematically, scalar multiplication is defined modulo minus. It's defined on equivalence classes under exchanging the sign on the point, which for us means exchanging the y coordinate, replacing y with minus y. So the equivalence class of a point p and it's negative. So what we're seeing here, it's just represented by the x coordinate. Okay, both these points have the same x, and if you take an x, there's only two y's that go with it. Okay, and they're both here in the equivalence class. So you can really label your equivalence class, work with it like equivalently just by working with x coordinates. Projectively, what we're going to say is the x coordinate of x, y, z is the pair xz here. Okay, because remember, the individual coordinates don't have values, not well-defined values. They can just be 0 or non-zero, but their ratios have an actual value. So the x coordinate of a projective point is the ratio of its big X and its big Z. All right. When the Z is non-zero, we can't use that for the point at infinity because its X and its Z are both 0, so they don't have a ratio. That's sort of undefined. So instead, we use 1, 0 for the point at infinity. So the projective representation of an X coordinate is XZ, and the projective point at infinity is 1, 0. But most of the time, it looks like we're just throwing away y. And the advantage then is that, well, first of all, we save a little bit of space by not dealing with y coordinates ever. All right. So I mean, occasionally this is an important saving, and we'll see that you also save a lot of time. I mean, it's obvious that you'll save some time if you never compute the y-coordinate of the result. Okay, if you're not using y-coordinates, then there's a bunch of things you don't have to compute in your group laws, for example. But what is interesting is that we can do without them completely and still save even more time than you think. Okay, so the protocol is now going to be, Alice is going to compute this mapping here, right? So given the x-coordinate of the base point, so the public generator, and her secret scalar A that she sampled, what she needs for her public key is x-coordinate of A times P. She has the choice, if she wants to, of, given the x-coordinate, choosing one of the P's that has that x-coordinate, basically recalculating one of the y-coordinates, multiplying it by A, then throwing away the y-coordinate of the result to get this x here. Okay, she could do that, but she might have a better option. In terms of specifying the protocol, this is what she's doing. She's got x of the base point, she's got a secret scalar, and she wants x of the multiple, which mathematically is well defined. Bob's doing the same thing. And then after that, Alice is taking the x-coordinate that Bob publishes and working out the x-coordinate of what used to be the shared secret in the plain group-based Diffie-Hellman protocol. But that x-coordinate is going to be the shared secret here. Bob's going to do the same thing, or at least something equivalent. And then they're going to hash the result and derive an AES key out of this. Okay, so you want to check that this is well defined. And then we've got this, this other sort of obvious question, which is, so far this just looks kind of like compression. Okay, you think, okay, well, they don't really need the y-coordinate somehow. You know, like there's only one bit that they're losing when they throw the y-coordinate away. So probably most of the interesting part of the discrete log and all that and Diffie-Hellman is already happening here on x-coordinates. But this would just look like compressing your keys unless there was some convincing reason for like if there was an algorithmic advantage as well. Can we do this pseudo scalar multiplication operation without using the group law? Okay, I mean, mathematically it exists. There's no group law involved. Can we somehow make this an effective algorithm? And we can. So x-coordinates don't have a group law on them. Okay, I mean, there's this ambiguity if we look at it like this. Okay, so now suppose we wanted to add P and Q, these 2 points on here, but we're only given their x-coordinates, which are these blue points on the x-axis. Well, if we're only given the x-coordinates, there's two pre-images for x of P. There's P or minus P, and we don't know which is the right one. For the x-coordinate of Q, there's Q and minus Q, and we don't know what the right one is. And if we just take all of the possible combinations and try them, we see there's this ambiguity where these 2 points together, what they do define is the set of x of P minus Q and x of P plus Q, but it can't tell us which one is which, right? So we don't have a group law. There's no geometric way of taking these two x coordinates and popping out x of the sum, but the x's of P and Q give you the x of the sum and the x of the difference as a pair. But what that then means is that if I have 3 of these blue dots, I can work out the 4th one. And that sounds like a kind of a stupid operation, you know, like you go, okay, well, instead of given x of P and x of Q, I get x of the sum, you go, well, x of P, x of Q, and maybe x of minus Q, and now I can get the sum. You go, well, when am I going to need the sum when I already knew the difference? You know, like this is kind of contrived and not very useful. It turns out this is exactly what you need. And you can do this in a way where you always know the difference, which we'll see. So writing this down sort of formally, any 3 of these x coordinates determines the 4th. So we can define pseudo addition, x-add, which given P and Q and x of the difference gives you x of the sum, and pseudo doubling, which is computing the x coordinate of a double. Here, P and Q are the same, so their difference is 0. So you don't need to know the difference. You know it's already 0 in this sense. It's sort of a degenerate XAD here. What we'll see also is that it's basically easier to identify and isolate and avoid special cases in the code for XAD than it is for the traditional group law. You don't have all these things like, oh, hang on, am I trying to add a point to its own negative? Or am I trying to add 2 points, but they're actually the same, so I need the tangent. Okay, you don't have to make all these decisions. It's you can write much simpler and faster code using these operations here when that's appropriate. So to optimize this and make the most of the techniques that we're going to show you, we'll use a different model of elliptic curve called a Montgomery model. And this is named after Peter Montgomery, who's one of the legendary figures of elliptic curve cryptography and computational number theory, and who sadly passed away recently. It's one thing to sort of have things named after you, but the number of tricks and algorithms and objects in computational number theory that are named after Peter Montgomery is very impressive. And it's basically because every time Peter Montgomery shows up and does something, he just did it the right way the first time. So when you look at his algorithms, it's really mind-blowing how simple and effective they are, and how hard it is to really improve on them years and years later. Anyway, so Montgomery was using this idea of working with only x coordinates to improve elliptic curve factorization back in the 1980s. So he was doing this at a time where elliptic curve cryptography had only just been suggested, basically the same year. But he wasn't really interested in doing cryptography. He was trying to factor stuff. And so when you're doing factorization, you're using big numbers. And in the 1980s, you were using pretty small computers for this. And so your ultimate game is to minimize the number of operations you do. Okay, you want to minimize the amount of arithmetic and the amount of work that you're doing. So Montgomery is optimizing elliptic curve arithmetic. He looks at Lenstra's elliptic curve factorization algorithm and realizes actually all you need to factor is the z coordinate of a point at some point. Do a big scalar multiplication, then take a GCD with z and the number you want to factor. That's how Lenstra works. He goes, well, the z coordinate, to make sense, it's a ratio with the x coordinate, that works out, but you don't need the y. So why compute the y? That's only going to slow me down, and nothing in my algorithm needs it. Here in Diffie-Hellman, we've got exactly the same situation. There's no need for y, so why use it? So we basically use these algorithms that Montgomery developed for factorization in a new setting, in a setting where factorization is meaningless because we're working mod p over fp. So here is his model for the curve. It's still a cubic when you multiply through by x, but instead of x cubed plus ax plus b, it's x cubed plus ax squared plus x, and the b parameter is shifted over to the left. This curve has a particular symmetry, which is if you swap the x and z coordinates, then everything still works out. Okay, it's you have an extra involution on the curve, which corresponds to translating by a certain point of order 2. This symmetry of the curve is it's reflected directly in the algorithms that we use, in the formulae that we use, and then in the algorithms. So that's basically where the speed is coming from. It's coming from the nice shape of this algorithm, the fact that this quadratic here is symmetric in x and z, the quadratic factor on the right-hand side of the curve equation. So we're writing down this form for an elliptic curve. You're like, well, hang on, we just talked about this other form for the last hour. But you can always convert forwards and backwards using this map here. If you make this substitution, you'll be in a short Weierstrass model. So all of the theorems and stuff that we mentioned before, all of the theory still applies. It just transfers onto this curve with a change of coordinates. Okay, not every short Weierstrass curve can be put in this particular form though, because you don't always have this nice translation by 2 kind of symmetry here. Right. The really important parameter here is the a. The b is going to disappear shortly. Okay, so now to make all the formulae simpler, given a point P on the curve, I'm going to write xp, yp, zp for its coordinates, its projective coordinates. Q, we do the same thing. For the sum, I'm going to write x plus y plus z plus, and for the difference, I'll write x minus y minus z minus. It's just going to make all of our formulas a little bit more readable. And then the pseudo addition on this curve, this being the kind of the not quite a group law, given x of p, x of q, x of the difference, it'll give you x of the sum. It's this. You compute this difference and this sum in the field. Do the same with the x and z coordinates here. You then add the u and v together and square the result, subtract u and v and square the result, and multiply back in z of the difference and x of the difference. And what you get is, as projected points, this turns out to be x plus and z plus. You wonder where this comes from. This is basically 19th century mathematics. It's coming from the theory of theta functions. But this is a classic thing, which for this particular form of curve, these formulae work out particularly simply. If you try to do something like this on a short Weierstrass curve, it still exists, but the u and the v will be messier, essentially. That's the real issue here. So here, this is really kind of minimizing the amount of work you're going to have to do in order to compute xad by taking your curve in this form. Pseudo doubling is also very, very simple. I'll just show you quickly here. What you notice, if you look at the xad formula, is that the curve constants a and b never appear in here. They're completely irrelevant. It's the same xad operation for every single elliptic curve in Montgomery form. Where the curve constants appear is just here in the doubling. And what matters here is not the value of a, it's a plus 2 over 4. So when you're choosing your curve, you're going to want to choose a in such a way that, well, and b if you like, so that you'll get a secure group, but also so that a plus 2 over 4 will be a very, very small value so that multiplying by it is easy, right? So we'll kind of minimize the size of a plus 2 over 4. Okay, so pseudo addition, pseudo doubling, they're both very easy. Now we're going to plug them together to make something that looks like scalar multiplication. To do this, you need a differential addition chain. And a differential addition chain, I mean, an addition chain is something like double and add. Differential addition chain means that anytime you do a plus, you have to have already known the minus. You have to have seen this before. There are many examples of this, just as when you've got like traditional addition chains like double and add, you can always go faster than double and add doing other stuff, or slower. There's more than one way to skin that cat. And the same thing happens with differential addition chains. But the classic example is again named for Montgomery. And he described it basically in combination with xad and xdouble and with this model of curve in the one foundational factoring paper. It's called the Montgomery ladder, which is one of my favorite algorithms because it's just kind of so neat and everything is just exactly where it needs to be. This is the simplest differential addition chain. It always works. It's the easiest to write down. And it also ends up being important for security in its construction, which we'll see a little bit later. Okay, so for double and add, you have for any scalar multiplication, you've got your input scalar in its binary expansion, and you've got the point p that you want to multiply, and the output is going to be m times p. So in double and add, you had just one temporary variable or one register, which we called R. Here we're going to have two, R0 and R1. I'm going to show you this algorithm in the group first, and then we're going to turn everything into x coordinates afterwards. Okay. But in the group, it's simpler to see that it's really working. So we have two sort of registers, one which we initialize to 0 and the other to p, 0 being the point at infinity, if you like. Okay, well, the identity element of the group. And then again, you work from the top bit of the scalar down to the bottom bit. In double and add, you always double and then you add if the bit is 1. Here, what we're going to do is if the bit is 0, then we double R0 and we add R0 to R1. Here, this is done in parallel, if you like. So, and if the bit is 1, then we do it the other way. The sum goes into R0, we update R0 with the sum, and we update R1 with its double. So the way to remember this is you think, okay, well, the value of the bit is just controlling which one of these two gets doubled, and the other one's going to get the sum. Right? So if the bit is 0, you double R0, and R1 is going to get the sum. If the bit is 1, then you double R1 and R0 is going to get the sum. Right, so this time your loop invariant, the thing that's always true here is that R0 is holding the value of, well, this truncated scalar value, just the way as it does in double and add. So actually, if you just track R0 through this, you find that what you're doing is double and add. All right. And the reason why this is happening is there's this other invariant over the whole algorithm, which is that R1 is always R0 plus P. I mean, it's initialized that way, but then you see every time you do an update here, so here R0, R1 is becoming 2R0, R0 plus R1, and if you take the difference of these two things here, you see that R1 is again R0 plus P. If the old values had this difference, then the new values still have this difference. The same happens in the other branch here. Right. So R1 is always P more than R0 the whole way through. And with that in mind, you see that what you're really doing here is double and add. And so at the end, R0 will be M times P and R1 will be M plus 1 times P. And you think, well, yeah, but you know, I mean, that's great. You managed to compute M times P plus P doing this really fiddly thing. I mean, that was obviously harder than just computing M times P in the first place. But the important thing about this, and what's going to let us map it onto x coordinates instead and to use the much simpler x-add and x-double operations, is that since we have this invariant, R1 always being P more than R0, the difference between R1 and R0 is always fixed, and you know it in advance, right? It's P, it's the input to your algorithm. So what that means is that anytime we want to do a plus here, we know the difference is P. The same goes here. So now we can replace all these pluses with x doubles instead, with x adds, and the doubles with x doubles. And the third argument to your x add in each case is x of P. You always know it. It's one of the inputs to the algorithm. Okay. So now it looks like we're doing a double and add with every iteration, with every bit of the scalar, because we're going to be doing either x double or x add. No, we're going to be doing them both. It's just a matter of which inputs we're putting where. Okay. So it's like a double and always add in that sense, but it's an x double and x add. Okay. So this is going to give us the x coordinate of M times P, and it's also going to give us the x coordinate of M plus 1 times P as a second optional return value. We're going to return x of M times P because that's what we want. But it turns out that given, just as an aside, given x0 and x1 here, and also given the y coordinate of P, you can work out what the y coordinate of M times P is. So you can actually use this to do scalar multiplication in a full group if you want, or in a full elliptic curve group. You do this, you use this very, very simple algorithm, and then you just recover the correct y coordinate at the end using a really neat trick. So this is a very useful algorithm even outside of Diffie-Hellman. Okay, so how are we going to actually use this? You're using this already. Basically, anytime you're using WhatsApp or Signal or you know, Chrome, then you're already using this kind of a key exchange. And it's formalized as a thing called X25519, which is basically our state-of-the-art Diffie-Hellman. This is what's standardized for TLS 1.3, but it's used in a lot of other applications as well. Now, X25519 is based on Dan Bernstein's Curve 25519 software, which goes back to 2006. And it's formalized in this RFC here. So you can go and you'll find all these algorithms kind of written out in a very engineer-friendly form there. We're just trying to explain where that came from. Okay, so Bernstein's software, this is in 2006. Remember, Montgomery came up with this approach to scalar multiplication in 1986. Okay, well, at least that's when it was published. He was already doing it before that, obviously. So when you go back and you look at Victor Miller's, one of the two foundational papers of elliptic curve cryptography, Koblitz and Miller both published the idea more or less at the same time, independently. at the end of Miller's article, there's a paragraph saying, well, actually, all of this works with x coordinates. You can just do it with x coordinates. But Victor Miller kind of explained this using like an even the scalar multiplication using some kind of funky recurrence relations, which makes it all a lot less obvious. And I think the cryptographic community basically read the paper and went, well, okay, that's all very mathematical. And it's also pretty out there, these elliptic curves. We might get to that x coordinate thing a bit later, and then forgot about it. So 10 years passes, and before, apart from point compression, before people are really doing this, 10, 20 years before people are really doing this, this x-only stuff. But Bernstein, I mean, he knew the cryptographic application. He was motivated by producing the fastest key exchange software out there. And being someone that had done factoring, he also knew Montgomery's work. So he knew like exactly the components that you need are already out there, and it's just a matter of putting them together and choosing proper parameters for this. And that's what this what his software achieves. Okay, so it only took 20 years for this to kind of take hold somehow, or to be sort of produced in an up-to-date way. And then it took another 10 years for people to get around to standardizing this, basically because Google and Apple started using it in advance. Okay, I will argue that this is a massive upgrade on traditional elliptic curve Diffie-Hellman for a whole series of reasons, which we'll see. Partly the software is so much simpler, partly it's a bit safer, and it's also faster, so why wouldn't you? Okay, so the elliptic curve in question, there's one elliptic curve used in X25519, and it's this curve called curve 25519. You can't fault the quality of Dan's work, but it's not the most poetic names. Anyway, the prime involved in the field is 2 to the 255 minus 19. Okay, this prime has been chosen because you can implement arithmetic mod this p in a very efficient way. The curve has order 8 times a prime, it's prime r. So you're not losing much security from this 8, but you're going to gain a lot of speed from it. Because, well, there's also the quadratic twist, which is this kind of shadow of your curve with a non-square b here. Here, the important thing, as I was saying before, is the parameter a, 486662. If you add 2, you get a multiple of 4. You divide through, and you can see this is a small integer compared with p. So it's quite easy to multiply by this. All right. So we've got these two curves working together. The idea of these two curves, the curve and its twist, is that if you take a value x, then either it's the x-coordinate of a point on E, or it's the x-coordinate of a point on E prime. Basically, if you evaluate the right-hand side here in Z, then you can solve for y if what you've got is a square. If it's not a square, then you can solve for a point on the twist instead. Okay, so we've got these two curves kind of operating in tandem, but they both have a large prime factor in their order. Okay, so they both have hard discrete logs, and therefore presumably hard Diffie-Hellman problems. Then we have the X25519 function, which, given an integer and a field element, maps you back into the field, well, or some encoding of field elements, which is fixed in the RFC. Given point U, which is going to be either x-coordinate of the base point of the curve generator or a public key, it's doing a pseudo-scalar multiplication. Okay, so it's defined in this way. It's like you take the point with whatever y-coordinate, which is either on the curve or on the twist, you multiply by m. You then just grab out the x and z coordinates of this. You invert the z coordinate using like a Fermat method here. So you power it to the p minus 2. Remember that powering to the p fixes your elements. Powering to the p minus 1 gives you 1 in a finite field, and powering to p minus 2 is therefore inversion. This lets you invert z, and if it's 0, then it doesn't fail. It just gives you 0 back, and it does all this in a constant time predictable way as well. So what we're doing here is essentially computing x over z, okay, which is like a normalized output value for this pseudo-scalar multiplication. Okay, I didn't tell you what the base point was. It's 9. Okay, so in the part where you're doing your key generation and x of p is fixed the whole time, here that x of p is 9. And it's very easy to use 9 in your scalar multiplication algorithms. Anytime you're multiplying by 9, this is much easier than multiplying by a general element of fp. Or if you're adding 9 or subtracting 9, same applies. Okay, the scalars, there are some restrictions on them. Basically, the bottom 3 bits have to be 0. That's what this 8 is doing here. And the 254th bit, or bit 255 in that position, has to be 1. So that means that all of your scalars have the same length in their bit representation. There are no short scalars. They're all this long. They've all got 3 zeros at the bottom. They're all multiples of 8. That means that when you go back to looking at these curves, even if you try to put in a point that's not in the right subgroup, that's not in the prime order subgroup, it'll be killed by the scalar multiplication. So any attempts to manipulate the inputs will be basically crushed by the form of the scalar. And Alice and Bob just use this x25519 function to do their Diffie-Hellman key exchange. Right? It's just used exactly as if it were scalar multiplication in a group. Okay. So one thing that I haven't mentioned yet, but which is very important, is side channel attacks. So think of timing attacks, for example, or power analysis if you like, but timing attacks will do. This means that if your algorithm behaves differently based on secret inputs, you'll be able to derive some information from things like how long it takes to run the algorithm. Right? Like, so double and add is a classic example of this, where if you just look at the time that it's taking to do double and add on a full scalar, you can probably guess how many adds there were in it, especially once you've seen a few double and adds. So what we need to do is come up with algorithms that are uniform and constant time, basically things where when the scalars are secret, you're never branching on their bits, okay? You're never branching on any function of a secret scalar. So there's no if statements on here. So there's no conditional code based on these things. And you're not allowed to have any memory accesses indexed by secret bits either. So you can't go doing like table lookups based on secret bits or functions of secret values. Ultimately, what you want to have is exactly the same sequence of instructions for every possible secret input. And it's maybe not obvious that this is something that you can achieve, but this is something that's crucial, basically. So when I say that this is important, and it's something that we want to anticipate and take into account, I'm not saying that the resulting algorithms are like side channel safe or that they can't be attacked. It's just that when you're designing algorithms and when you're implementing them, you have to assume that you will be subject to side channel attacks. And so you have to do your best, right? It's your duty to try and avoid or mitigate timing attacks and power analysis. And that's about the best you can do. After that, it becomes someone else's problem further down the hardware chain. So we've got to do our best. We have to turn our algorithm into the same sequence of computer instructions. Otherwise, we're clearly broken. And when you look at the Montgomery ladder, you go, well, what do you have to do to this to turn it into something that's uniform and constant time, something whose running behavior is completely independent of the secret. The secret in our case is not the point. The point is either, or the x-coordinate, is either the generator or it's someone's public key. Okay, so we can do whatever we want with respect to the x-coordinate, but the scalar, that's someone's secret key. It's always Alice's secret key or Bob's secret key. So we're not allowed to do any ifs or any lookups based on bits of m. And then when we look at the Montgomery ladder, we see, okay, well, in each iteration, we're doing exactly one x double and one x add. Okay, so the amount of work we're doing per iteration is exactly the same. There's no variation according to the bits of m. Although we still have this if statement. We are actually branching and doing one thing or the other based on a bit of m. That looks bad, right? But when you look at the operations that you're doing, you see that that bit is just controlling who got doubled. And then the same two inputs are going into the add. Okay, so what we can do instead of using an if here is we can use a constant time conditional swap, which is a function which, given a bit and a pair of values, will return either the same pair or the pair swapped over, just depending on the value of the bit. And it will do that without any conditional code. If we do that, then we can basically just, we'll say, we're just going to do this one line here, this x double on x0 and x add here, but we will swap x1 into the place of x0 if required, based on that bit, and then swap it back out again. So there are lots of ways of doing this. The simplest way, at least, well, I mean, you can do it using bit operations in parallel, or you can think of it in a bit like a homotopy kind of way, where if your bit is 0 or 1 as an integer, you can do this using just plain old arithmetic operations, multiplication in FP and addition in FP. Clearly, 1 minus b is going to be 1 if b is 0 and 0 if b is 1, and vice versa for b. So applying these formulae, when b is 0, you're going to get x0 in the first coordinate and x1 in the second. And when b is 1, the x0 will be masked away and you'll get the x1, and you'll get x0 in the second here. So that will swap things over. And then the simplest way to adapt your Montgomery ladder is to do it this way. Remember, we had this if before, and we just plug in a conditional swap. So we swap based on the bit. If it's 1, this will switch over x0 and x1, which makes sure that x1 is being doubled instead of x0. But it's being placed into the x0 variable, so then we're going to have to swap this back to get things in the right order afterwards. You can check that if mi is 0, this is doubling x0 and adding the 2 into x1. You can also check that if the bit is 1, then you're doubling into x1 and x adding into x0. This is not optimal at all. I mean, it's pretty simple to see that you can cut the number of swaps in half here, basically just by composing the last swap with the first one. Then you need an extra swap outside the loop, either to get things in place in the right place at the start or to get them into the right place at the end. But I think this is at least the simplest way to see what's going on here. And having done this, you can see that when you're applying this to x25519, the parameter beta here is 254. Okay, so no, is 255. So the number of iterations is fixed. The sequence of operations you do is completely fixed. So this algorithm will run identically no matter what scalar you put in. It's just that then these conditional swaps will make sure that everything interlaces properly and you end up doing a different scalar multiplication. Okay, so we have a short amount of time, maybe 15 minutes, to look at something completely different, which is elliptic curve signature schemes. And these are something that's very, very useful. The most widespread elliptic curve signature scheme, coming up to the present day has been ECDSA, which is kind of spectacularly ugly. And what we're looking at in some protocols now is more like EDDSA, but this is based on Schnorr signatures, and Schnorr signatures are kind of the simplest way of presenting this stuff. They're definitely the simplest signature algorithm which you can use with elliptic curves. It's kind of the right way of doing things, so that's what we're going to look at. And then in the bonus tracks, there's details on EDDSA, there's details on ECDSA if you want, and there's also something on multiscalar multiplication, which you need to implement these things. All right, so signatures. Again, your keys come in matching public-private pairs. They're discrete log-based keys. So Q is X times P, where Q is the public key, X is the private key, and P is a fixed generator of the group base point. So here, if you want, for the next while, you can think of this as being not necessarily in an elliptic curve, but just in a generic group. So we're going to start this off by presenting an identification scheme, and then we apply the Fiat-Shamir transform, and we end up with a signature scheme. And having an identity basically just means being distinguishable from everyone else. It means you've got something that no one else does. And so in our case, you know, the question of what identity is in a cryptographic sense, having an identity is holding a secret key. You know, that's something that you have and no one else has. Holding a private key, it's private to you. Okay, so it's holding that, and you have to be bound to the public key. I mean, if you're holding a private key and no one knows what the public key is, this is like, or that it's associated even vaguely with you. That's like, you know, like a tree falling in the forest and no one being around to cry or identify you. Okay, so having an identity just means you're going to hold a private key corresponding to some public key which you're bound to. And so to prove your identity, you need to prove to someone that you hold the private key. Right? Or if someone shows up and says, all right, I'm Alice, and I want to be sure that they're really Alice, I want Alice to convince me that she's holding the private key corresponding to what I think is Alice's public key. Okay, so in symmetric crypto, we have stuff like when we talk about authentication, we have like MACs. We've got authenticated encryption, and we use this all the time, and it's fast, it's efficient. The thing is, this is going to authenticate data, but it can't authenticate the communicating parties, not on its own. And the reason for this is kind of simple. It's that when you're doing symmetric crypto, both sides hold the same secret. Okay, so Alice and Bob, if they're using authenticated encryption, like AES GCM or something like this, or Cha-Cha Poly or whatever, they can communicate in an authenticated way, but Bob can never really be clear that that was Alice at the other end, because Alice could have given the same secret key to someone else. Okay, I mean, it's shared, so it's definitively not an identity. So how do you prove your identity? We formalize this using 3 characters: the prover, the verifier, and the simulator. Okay. The prover needs to prove their identity. They need to prove that they know their secret key, their private key X. The verifier needs to verify the identity of the prover. So they want to find out if the prover really is who they claim they are. The simulator wants to impersonate the prover. Okay, so a simulator can take the place of the prover, and the verifier needs to know if what's going on. So the way this game works, the classic game, is as follows. Prover generates their key pair, and at some point they publish the public key. From that point, the game is essentially on. Whether or not they ever get around to proving their identity to anyone, as soon as their public key is published, people can start attacking it, trying to break it and to steal the identity. But at some point, verifier comes along later on and challenges the prover and says, all right, well, are you really Alice or Bob or whoever it is? And the easiest way for the prover to demonstrate that they know the discrete log of Q is just to give it away. So they could load the discrete log into S and publish S. The verifier can check if this really is the discrete log. They just multiply up the public generator and check if what they get is Q, right? And they could accept this, all right, as a proof that the prover knew the private key. The problem is that the prover no longer has any identity because they've revealed their private key. Okay, now the verifier knows it as well. So that's definitely no longer just the prover. It could have been someone that verified just before. Okay, as soon as the private key is given away, the identification is lost. So what we need to do is somehow prove that we know the private key without giving it away. And we can't give it away because it's long term. We want to use it more than once. We don't want to have to generate a new private key for every time we're trying to identify ourselves. So it's a long-term secret, and we're going to hide the long-term secret with an ephemeral secret. Basically, we've got something long-term we need to protect, and we've got stuff that we're prepared to throw away and use one at a time. So we're going to generate one of those things, an ephemeral secret, and mash it in with a long-term secret to hide it. And this is how we do that. As soon as the challenge from the verifier comes in, the prover switches on and generates a new key pair, big R and little r, which is ephemeral. So it's just for this exchange here. Okay, so it's a one-shot key. So they're going to publish the public key from that, and they're going to add the two private keys together. So remember, these are scalars, they're integers in the elliptic curve context. So we're going to add these together, x and r, and publish the result s. Now the verifier can multiply up s times p, and then they can also take the two public keys and add them together, and they're basically just checking if the sum of the private keys is the sum of the public keys. So the prover is revealing this R and committing to it in that sense, and then also sending this S. And the idea is that S is revealing nothing about X because R is random. If you take some value and you add a random integer to it, what you've got is a random integer, basically by definition. So the verifier is going to accept this because adding scalars is the same as adding multiplied points. So S times P is X plus R times P, which is XP plus RP, which is Q plus R. So this is correct. The problem with this is that you can cheat. All right. So if the verifier gets this, they'll be like, all right, yeah, well, that's definitely the sum of the discrete logs of these two things. Don't know these. How do you cheat with this? Okay, you're the simulator now. The public key has already been published by the prover in the past. The verifier challenges, and you step in and you impersonate the prover. You generate your key pair, R prime and little r prime, but this time, instead of publishing the legitimate public key R, you publish something that the verifier will see as a public key, but it's R prime minus Q. So you've taken the public key and subtracted it off. And then you're setting S to be little r prime, the discrete log of big R prime. Why are you doing this? Well, you don't know what X is. So you can generate an ephemeral key, but then you can't go, you don't know the discrete log of the sum, because you know your own discrete log, but you don't know the prover's discrete log. Okay, so the simulator here, when they're cheating, they don't know the discrete log, but the really key thing here is that they don't know the discrete log of the point they've published either. Okay, so they've sent out this point R, but they don't know its discrete log. The verifier doesn't know that. They take R and they take Q, they add them together, and what they're going to get then is R prime, big R prime, and so the S that they see is going to be the correct discrete log, and they're going to accept this so-called proof. So this is no good, okay? What we're finding here is like, how can you tell the difference between a prover and a simulator? Well, you think about what they know. A prover is sending the sum of X and R, and they know both X and R because they made them both. A simulator is sending the log of Q plus R, but they don't know the log of Q and they don't know the log of R either. Okay, so the difference here is knowing X and knowing R. Okay, the prover knows both, the simulator knows neither. So the verifier would say, okay, well, I can't ask for X, okay, because prover won't give it to me, it's their private key. And you could say, well, I'll ask for the ephemeral secret instead. I'll ask for R. I'll ask them to prove that they know R. But if they give away R and she already knows S, then she'll find out what X is. So she can't ask the prover for R either. She can't ask for either of these values. So what we're going to do, well, I mean, instead, we'll say the verifiers are allowed to ask for either S or R. So either R or the sum, R plus X. And they'll check an equation accordingly. Why is this worth doing? Well, if they've asked for S and S is correct, then that means that the prover knows X if they're honest, if they're not cheating. If they ask for R and it's correct, then that means that the prover wasn't messing around, like the simulator really was the prover all along. They really knew R. Okay, so that means there was no cheating going on, but it doesn't prove that they know X because S was not involved this time. So you can either be convinced about X, but not honesty. So identity without honesty, or honesty without identity, but not both at the same time. So what you do is you just do heads or tails, okay? And this is Chom-Evitz and Graf that show this. So you choose a value E after the prover publishes R, okay? After they commit to R. Then you decide whether you're going to ask for little r or s. The prover responds accordingly, and you check accordingly. So to cheat now, the simulator is going to have to guess what E you're going to choose, because remember, they can't generate R honestly or not here. Okay, they have to guess what your E is in advance. So if you just do this enough times that they can't have possibly guessed, like 128 rounds, and then, you know, they'll have broken AES before they guess, then you can be pretty sure that they are who they say they are. The problem is that that makes your protocol look like this. And I've left out 126 rounds in the middle. You're just going backwards and forwards, sending points, sending 1-bit challenges, sending back scalars over and over and over 128 times. So this protocol, in a cute way, I mean, it's zero knowledge, okay? And that's independent of the number of rounds that's being carried out. Okay, I mean, the verifier learns absolutely nothing about the value of X at any time in this. But this is really inconvenient. Okay, there are too many interactive rounds of communication. You've got to be basically online for all this, just going backwards and forwards, 128 challenges and responses. You're sending much stuff. I mean, you think you've got 256-bit elliptic curve public keys, but instead you're sending 128 of these and 128 scalars. So this is kind of huge. And then everyone's doing a lot of scalar multiplication on both sides. So it takes a lot of energy, and it basically burns up the battery on your phone or slows your server down. So Schnorr's identification scheme is basically exactly this, except you do the 128 rounds more or less in parallel. You replace 128 individual 1-bit challenges with one 128-bit challenge. So E, instead of being a single bit and then doing this 128 times over, you pick a 128-bit string, but view it as an integer and continue as usual, just for one round. Okay, again, S is not really revealing anything about X here because R is random. This does everything in one round, but this time there's only one 256-bit scalar multiplication for the prover. The verifier is going to do, well, they've got to multiply up S, which is a 256-bit value, and they've also got a 128-bit E that they're going to have to multiply up here. This is not zero knowledge anymore. This is something we should make clear. Because the triple Q being the public key, and the S and the E, this is a particular solution of an equation. Like, this is a non-trivial solution to something interesting. So the verifier is free to choose E as a function of Q, okay? But it's reasonably clear, like if you look at it hard, it's hard to see that this gives you anything useful about X. So it's not like the verifier learns nothing. They just learn nothing that we know anything to do with from this protocol. Okay, so this is a Schnorr identification, and then you say, how do you turn this into a signature? Like I was saying, we apply a Fiat-Shamir, and we'll get through this, I hope, quite quickly. Then we can stop. So digital signature is a non-interactive proof that a signer saw or created, or, well, that they witnessed some data. Okay, so we need authenticity, message integrity, and non-repudiability. So only the signer can create this. Only the signer couldn't have made it from any other data, so the data wasn't modified. And only the signer's public key and the data are needed to actually verify the signature. And we apply the Fiat-Shamir transform to this. This is something which, if you don't know it, it's useful not just because you use it for elliptic curve signatures, but because it's one of the main tools that we use in theoretical cryptography to build signature schemes from algorithms. You make an ID scheme and then you Fiat-Shamir all over it, and there you have a signature scheme of some sort. So The Fiat-Shamir transform does this by making the ID scheme non-interactive and making the signer identify themselves to the data. So basically, the data is going to drive the verifier in this sense. And therefore, anyone can be the verifier and replay this verification because they've got the data for the signature they're trying to check. Okay, so the signer will play the verifier in the first instance using the data, and then everyone else that has the data later on can replay the same script. Okay, so here I've got a formal statement of what's going on, but my kind of informal way should make enough sense for what we're going to do here. Okay, so the intuition of this is that when the prover is publishing Q, R, and S, okay, the verifier normally has to come in here in the middle and send a challenge after R. They're going to send a random number. But how they're going to generate the random number, they're probably going to use something that looks like a hash function anyway to do this, a very similar algorithm. So they might as well literally use a hash output. And if the hash function is any good, then if they just plug in this public key R, the ephemeral public key, into the hash function, that's going to give them a random looking output that it should be kind of impossible for the prover to control. The prover can't really manipulate this. Okay, they can go around generating new key pairs and new key pairs and new key pairs until maybe they come up with a particular sort of challenge that they think might be suspicious if they were being manipulative. But that's just going to cost them a lot of work, right? This is just a repeated key generation and hashing. Okay, so verifier is probably going to hash something. So let's just say they hash the public key. That'll do. And then you've made this this identification scheme non-interactive, okay? Because if the prover knows the verifier is going to hash that, and the verifier knows, well, my hash function is pretty good, the prover couldn't manipulate this by choosing a bad R, then this is going to be fine, okay? And they'll be reasonably convinced of the identity. We don't really want a non-interactive identification scheme, and I'm not going to make any security claims about what we're seeing here. This is just a first step along the Fiat-Shamir path. So the second thing is, I was saying, you have to identify to the data. Here we've got an identification scheme. There's no data involved, so there's no signature. And so just before I say that, I also want to emphasize that generally, like in a lot of settings, the hash is a lot smaller than the public key, because the hash, you can take a 128-bit value, but if your public key is in like a finite field discrete log group, it's like 3,000 bits, which is way too big. So you can switch it around and send E and S instead of R and S. The verifier can reconstruct R using the relation that they would normally check. And then what they verify is that the hash is correct. Okay, so we can just twiddle this around a bit and come up with something more compact. And in classic Schnorr signatures, that's what you do. In elliptic curve signatures, that's slightly less relevant because you don't have this massive difference with the key size. And in EdDSA, you'll see that they don't do this. Okay, so getting back to identifying yourself to the message, and then we're just about at the end. The message comes in here and you just hash it in with that public key. Okay, so now the challenge value E, which you're pre-computing, and which the verifier will end up with in the same way, it's derived from the hash of the ephemeral public key and the message together. And then S also depends on the private key. So now you have an actual signature scheme here. If you change the message, you can see that you'll mess up the hash, all right? And that'll invalidate the signature. If you don't know the private key, you can't get the right S, and that'll mess up the signature. Okay, or if someone sticks in the wrong public key, it won't fit with X, and then you'll mess up the signature. Okay, if you want security proofs for this, it's secure in the random oracle model. It appears to be reasonably secure in practice. It's not secure in the standard model. Why am I explaining this and saying it's not ECDSA when lots of people have been using ECDSA? It's basically because this was patented, and cryptography sees patents and mostly roots around it, essentially. So why would you pay to use this when you could use a kind of mangled version of it like ECDSA instead. But now the patent's expired, so we can use Schnorr signatures again. And so basically all curve-based signatures that have been derived in the last few years have been Schnorr variants like EDDSA. EDDSA, there's a bonus track full of this, which explains exactly how it works. There's also one on ECDSA if you want to see the difference between this and EDDSA and pure Schnorr signatures. And there's also an important algorithmic trick. Here it looks like you need to compute S times P and compute E times Q and then take the difference. In reality, you compute this all in one go, mutualizing a lot of the calculations in those scalar multiplications, okay, using a multi-scalar multiplication, which is another useful algorithmic trick to know. So we'll stop here. And again, I'm around for questions. I'm going to be around on Zulip for a while, and then throughout the week, I'm happy to discuss all this stuff. Also to discuss this with live Q&A now if there's any particular questions. But the things that you want to remember you saw just now, the really key things, first of all, is X25519. You've seen how we really do elliptic curve cryptography. It's not just to take your elliptic curve, plug it in as if it was a group and use the textbook protocol. We really use the features and geometry of the curve to come up with something extremely efficient. Algorithmically, you want to remember the Montgomery ladder, which is a really useful tool even outside X25519. It's useful all over the place anytime you want a constant time scalar multiplication for elliptic curves, or you want to do factoring. It's also just a really neat algorithm once you've checked the invariance for yourself and you've convinced yourself that it works. Finally, you want to see that elliptic curve signatures are fundamentally very, very simple. They're based again on scalar multiplication and manipulating the scalars, adding them in this case, and you just need to plug in your hash function in the right place, Fiat Shamir the whole thing, and you've got a compact, legitimate signature scheme. Here you can see the public keys here. There's a 128-bit scalar and a 256-bit scalar, or it could be a 256-bit public key. You could publish R instead of E and S. But these are very short signatures in that sense for still giving you 128 bits of security. Anyway, again, we'll stop here. Let's go on about 5 minutes longer than I was hoping for. If anyone is still awake or alive, I'm happy to go with questions. But you can also post questions to Zulip during your lunch break, if you prefer, or afterwards. And we'll catch up. So I'll stop the share so I can actually see chat and Zulip.
So, thank you very much.
I can see one question.
Is there any